If you've ever dipped your toes into computer graphics, if you've spent any time trying to render anything beyond a simple triangle in 2D, you know the feeling. You write code and it works. Until it doesn't. The problem? We were stuck in the past. Hello there and welcome to yet another episode of my OpenGL series. Remember the code that we wrote in a previous video? We were not using any features past OpenGL 1.1. Yeah, we wrote almost the same code that programmers used to write almost 3 decades ago. All the way back when flagship GPUs had just 4 megabytes of VRAM. Those ancient GPUs could barely handle 100,000 triangles. With every single GL vertex or GL color command, the CPU would tell the GPU to take into account yet another vertex or change the color of the next vertex. Always remember that CPU-GPU communication is very expensive and we want to minimize it as much as possible. The PCIe lanes simply can't transport data as fast as the CPU and the GPU can process it. This creates a bottleneck. In legacy code, the CPU passes the same data to the GPU every single frame. The GPU has to free the memory from the previous frame, allocate new memory, and put the same data in the newly allocated memory. The solution to this bottleneck is quite obvious. We allocate a blob of memory, fill it with the vertex data, and pass it to the VRAM before the render loop starts. In every frame, we tell the GPU to draw using the provided data. This is called issuing a draw call. Memory buffers are nothing more than temporary memory buffers or chunks used to store data, just like the one I mentioned. Since we use this particular memory buffer for storing vertex data, it is called a vertex buffer. There is a misconception I want to clear before we begin coding. Vertices are more than just points in space. Besides position coordinates, they can also have texture coordinates, color information, and a lot more. These are called attributes of a vertex. We have looked into the logic of things. Now let's look at the code. This right here is legacy OpenGL code. We know that just by looking at it. If GL begin and GL end exist, there is legacy OpenGL code. Now to actually begin, we'll create an array of vertices. Now we need to generate an ID for the buffer. I've named this variable as VBO because it stands for the ID of the vertex buffer object. That is what it stands for. We use the GL genBuffers function. Here, n represents the number of buffers that we want to generate. Here, we just want to generate 1. And then the ID for the buffer. Since OpenGL works as a state machine, we don't actually have to specify to the function every single time which resource or buffer we want to use. It will by default use the selected one. Here the selected buffer is called the bound buffer. And the process of selecting it is called binding it. We use the GL bind buffer function to do that. The target is GL array buffer and the actual buffer ID is VBO variable. Now that we have bound this buffer, we can actually use it. First, let's assign the raw buffer data to it. We do that by using GL buffer data function. The first argument is target, which is GL array buffer in our case. Size here represents the number of bytes that the buffer occupies, which in our case would simply be vertices.size times the size of the first element of the vertices. Now I've adopted a completely modular approach so that even if I change the data type, it would remain same, and if I change the number of vertices, it will still remain the same. I don't have to change a thing in here. The next parameter here is the data, which would simply be vertices.data, and usage is GL static draw. Now we know what kind of data vertices represent. It's 2 floats, each for each vertex. But it could be a 3D vertex as well, and it would have 3 floats for each vertex, and in total it would have just 2 vertices. How does OpenGL know what layout we're using? Well, we need to explicitly specify which layout we're using, and we do that by using GL vertex attrib pointer function. The first parameter here is the index of the attribute. If an attribute appears first in the layout, it would have index 0. If it appears second, it would have index 1, and so on. Since we only have just one attribute, that is position coordinates, it would just be 0. The next parameter is size. This is not the size in bytes, it's only the count of floats that we use for this particular attribute. It's 2 for our case. Next up is the GLenum type. We need to specify what type of data we are using. In our case, it's float data type. We also have normalized coordinates in our case. Now stride here represents the number of bytes between 2 consecutive vertices. In a simple format like this, where we have position coordinates only, it would be 0. If we had a very unusual layout where we had one array for position coordinates, another for UV coordinates, another for color coordinates, then we would have to set the stride accordingly. In our case, it would simply be 0. The next parameter is called pointer. What does it actually represent? Well, it is the offset of the current attribute from the starting of the vertex. Since we only have just one attribute, it would just be 0. We need to actually cast it as void pointer because it represents a pointer data type. Finally, we call GL enable vertex attrib array function and pass it 0 as the index. For now, we'll just remove the legacy OpenGL code from here. That's gone. And to use these, we simply call GL draw arrays function. The mode is GL triangles. The first vertex is at index 0 and there are 3 vertices. Note here that we did not specify which vertex buffer to draw from. OpenGL will automatically use the one which is already bound. Great, now let's run the code. And here we see a beautiful white triangle. Well, that's it for today. In the next one, we'll explore more about shaders. If you found this video helpful, please like, share and subscribe. I'll see you in the next one.